second speaker for the afternoon, Dr. Sirui Li. She's a senior research engineer at Microsoft Research in the machine learning and optimization group. Her current research focuses on the intersection of large language model and optimization, aiming to improve optimization to be more accessible, interpretable, and reliable. She finished her PhD in social and engineering systems and statistics at MIT here, where she was advised by Professor Casey Wu on machine learning for combinatorial optimization. Her doctoral research developed learning-guided algorithms to accelerate large-scale combinatory optimization solvers, as well as control sporadic and reinforcement learning methods for mixed autonomy transportation systems. Now let's welcome Sirui.
All right. Thanks for the introduction. My name is Sirui Li. I'm a senior research engineer at Microsoft Research. So today I'm going to present OptiGuide. This is a recent framework developed by a group at Microsoft Research around the topic of GenAI for optimization and decision intelligence. So let me start the talk by presenting a bit of background about my group for you to better understand the scope of projects that we do. As the name suggests, we work at the intersection of machine learning and optimization. So a lot of our recent work revolves around two big themes. The first one is cloud efficiency optimization. This is about how we can optimize cloud operations from a supply chain perspective. So for example, how do we place infrastructures in data centers, or how do we schedule virtual machines? And then when we start doing this, and especially when we interact with supply chain planners, we get demands for explainability, automation, and the business planners always want us to make the interaction with them more easier. So all those demands kind of motivates our second and more recent direction of research, which will be the topic of today. And this is about how do we combine generative AI and optimization tools to automate and improve decision-making in this framework, which we call OptiGuide. So our group starts the OptiGuide project when we were working with our customer Zero, which is Microsoft's own cloud supply chain. This is a supply chain that aims to bring efficient hardware in Microsoft's data center in order to keep up with the increasing demand for Azure and other compute services. Under some demand projections, there are a lot of decisions that the supply chain planners need to make. So for example, which supplier should we choose? When do we schedule transportation of a certain demand from the supplier location? And also, what physical location in the data center should we place racks of servers? So in particular, the input to the fulfillment problem that we study, it has a set of demands over a planning horizon of a few months. So each of the demands come with an ideal dock date, which the data is should be ready to deploy, and also a region where it should be placed. Each demand can be scheduled through different options of suppliers or manufacturers, server manufacturers. Selecting a supplier for each demand need to consider many different aspects, such as supplier capacity, and when the hardware will be able to ship from each supplier, and also the shipping costs from the different warehouses. And on top of that, we also need to choose a data center where each demand will be docked. At the same time, we also must select an adequate dock date and coordinate different shipments so that we don't run into throughput bottleneck at the data center. So this leads to a very complicated optimization problem with many different constraints and objectives. And it's very hard to be solved. So I've touched upon a lot of the constraints there, and also for the objective, we have different things like delay costs if you schedule too late, idle costs if you schedule too early, deprecation costs, and shipping costs. You can see all those different components in the optimization problem make it very hard to understand and solve. When we started in the space, a lot of these decisions were made manually. So the first step through automation was that we developed an optimization method that modeled this problem as a mixed integer program. In fact, we designed and deployed this optimization service which we called Intelligent Fulfillment System, or IFS, in real production. So by running the optimization solver, we're able to generate the optimal supply chain plan, and then the supply chain planner can take the plan and execute it. In fact, we're able to deliver thousands of racks per month to hundreds of data centers through this optimization problem. We're able to automatically generate a lot of fulfillment decisions and add a lot of flexibility to the system. In particular, we substantially reduce the cycle time, or in other words, the amount of time it needs for the plan or for the hardware to actually live in data centers. And this can translate to cost of savings of tens, hundreds of millions of dollars per year. So this is a great start. However, there are still a lot of challenges. The first thing, as you have seen from the previous slides, this is a very complicated optimization problem with many different constraints and objectives. So this is very hard for especially non-experts to understand what's actually going on. And also, things happen. So new demand may come into the system, or there may be shipping delays in the system. So all of these changes require constantly resolve the optimization problem. And furthermore, this is a very large optimization that we're solving. So you can imagine at a Microsoft scale, there are thousands of racks per month that need to be scheduled over hundreds of data centers. So given this complexity, it's not that easy to understand exactly why this decision is being made. And supply chain planners that interact with the solution may have a lot of questions. So for example, why is a certain demand not fulfilled? Or why do we choose a certain supplier Y for demand X over another supplier Z? So let's consider this concrete situation. Suppose you are a supply chain planner, and you see that a demand 1 is assigned to supplier A instead of supplier B. And you want to ask the question, why don't we use supplier B for demand 1 instead? So we can do a counterfactual study and study what will happen if you assign supplier B to demand 1. But in reality, simple changes like that can typically trigger a very complicated downstream effect. It's very hard to be fully considered by the supply chain planner. So for example, there may be another demand 2, that's already assigned to supplier B. So if you want to switch supplier for demand 1, you need to also switch supplier for demand 2. Suppose you switch to supplier C for demand 2, you may see there's another conflicting demand that was already assigned, so you need to make change there as well. At the same time, the change of supplier may trigger a delay in the docking of the demand, say if the supplier is far away. But due to a throughput constraint in the data center, another demand that was scheduled to be docked on that day may now have to be moved in a different data center because we don't want that schedule to be delayed. However, for that data center, there may be already a lot of other demands as well. So you can see that we need to make constant changes just because we make the simple change in the beginning by assigning supplier B instead of supplier A to demand 1. And this sort of domino effect can end up affecting a big part of the supply chain plan. As you can see, it's very hard for supply chain planners to interact with the plan, either to understand why each decision is being made or to study different scenarios. In fact, for many of these scenarios, even if you just make a simple change, the supply chain planners may not fully understand what's going to happen, so they need to reach out to engineers or data scientists who implement these plans to see what's going on. And this a lot of times require multiple interactions between the engineer and the supply chain planners, and they can cause delays of over 2 days for them to fully understand a simple situation. So to address this challenge, we, in our group, designed OptiGuide, an all-empowered framework for interacting with optimization technology. So OptiGuide enables asking questions in English about supply chain plan, including what-if questions. Here is a block diagram of OptiGuide. The idea is the user asks a question in natural language, and we take a question and feed it through LLM to translate it in optimization code. So for example, if the user asks a question, what will happen if we dock a certain demand a week earlier? We'll feed this requirement into LLM, which will generate a new constraint that enforces earlier dock date. And then we'll run an optimization solver under the hood to generate the new optimization plan under this user requirement. After we get the solution, we will translate back the solution into human understandable natural language for the user to decide whether they want to execute or not. So a few points mentioning about OptiGuide's design. First, when we started this project, it was a few years ago when GPT-4 was released, and we see surprisingly, even with GPT-4 and in-context learning, we were able to achieve very high accuracy. And with the new development of GPT-5, GPT-5.2, the accuracy got even higher. And more importantly, from a security standpoint, the data of the user, for example, the data center plan or the demand information, stay in-house. So it's relatively safe because the user don't need to expose all those information to the LLM. LLM themselves only see the constraints and objective of the problem instead of the raw data. In fact, through OptiGuide, we're able to reduce the answer time from days to just a few minutes, and drastically improve the efficiency of the system. So let's look at a demo of OptiGuide. Here, the user will initiate an interaction such as asking a question about dock date. OptiGuide can then generate insight and then recommendation give to the user to decide what to act. So let's look at this demo. So here, the user asks a question about a dock, whether they can dock on this date, and then OptiGuide say, oh, you can, but there's it's less efficient, and you will incur this extra cost. And then based on that, OptiGuide gives recommendation to the user to do whether to act on it or not. Going beyond the example of cloud supply chain, our vision for OptiGuide is to help decision makers to make decisions across the board. So users may work on different application domains, for example, supply chain or workforce scheduling, production delivery, or many other applications. OptiGuide combines generative AI and optimization tools to help users interact with the data and tools. Our goal here is not for generative AI to replace optimization, but rather to work with it end-to-end together for decision intelligence. And recently, with a focus on data privacy, security, efficiency, or simply to reduce cost of API queries, a lot of business planners start looking at ways to fine-tune their open source LLMs to host in-house instead of calling third-party API queries. So the benefits here are you can save a lot of costs because you don't need to pay third-party LLM companies for these queries. And more importantly, this adds another layer of security because not just the data that you don't need to send to the LLM company, but now the optimization problem, including the constraint and objective, you can store them in-house instead of giving to other companies. So to advance on this front, we have designed a few methods to better fine-tune small LLMs for optimization modeling and solving. So here I'm going to present two projects related to this direction. So this first project is titled Towards Foundation Models for Mixed Integer Linear Programming. It was done around 1.5 years ago, and this project is about the topic of optimization data synthesis, the trained machine learning model that can generalize across a variety of different optimization problems. So the background for this project is that comparing with general LLM fields where abundant data has been used to train a lot of frontier models, such as GPT-5, optimization in comparison is a very specialized domain where very limited data have been made available. In fact, if you look at papers at the intersection of machine learning and optimization across many years, we see that all those papers typically study a very limited number of textbook-style optimization problems, such as shop scheduling, vehicle routing, or combinatorial auction. However, in real life, the optimization problem people study tend to be far more complicated and diverse than the things you see in textbook. So that motivates this project. How can we synthesize realistic optimization problem to broaden the diversity and coverage? And suppose we're able to generate those data, can we train a single model across optimization problem class to a lot of other unseen optimization problem class? So we hope that through training, we're able to generate this relatively general optimization LLM that can that can assist business users across many optimization domains. So in this work, we propose an LLM-based evolutionary procedure to generate optimization classes. On the right, we show a visualization of seed classes, which we use to start the evolution, which are shown in orange, as well as the finally generated optimization classes shown in blue. So this is a visualization in the code embedding space, and we can see that the generated classes span much diversity, basically cover the space given by the initial seed classes. And on the left, we compare the model trained on the generated optimization dataset versus just simply in the C class. And we see that across many different learning tasks, such as inequality gap prediction, learning to branch, and the language MILP alignment task, our model trained on our synthetic dataset is able to achieve much better performance than just training on C classes. So here is a pipeline of our method, which we name MILP Evolve. MILP Evolve starts with a small number of C classes, such as traveling salesman, facility location, or vehicle routing, and we prompt LLM to evolve those C classes to better diversity and complexity. In fact, this is done by delivering different styles of LLM prompting, including adding constraint, mutate constraint, crossover to different optimization problem into a single coherent optimization problem, adding new components to optimization, or delete redundant components. Through these different styles of prompting method, we are able to generate a lot of different optimization code. And then we feed those optimization code into a filtering and parameter search procedure. This is because a lot of the code generated can be invisible, and for those code, we can filter them basically by running the code through the solver and see if they are feasible or not. And some of the code generated may be taking too short amount of time or too long to solve. So in order for the code to satisfy certain solver properties, such as solve time, we also developed this parameter search subroutine, which we basically change certain parameter in the code generated, such as problem size, so that the code can satisfy those solver properties to achieve reasonable solve time. After that, we repeat this procedure for many iterations on the newly generated code, with the hope that with more iteration of this evolution, the code we generated can be more diverse. So on this slide, we show a comparison between a C class and the generated MILP class. On the left, we see an independent set example, which is quite a canonical textbook example. So you have different nodes in the graph, and each one represented by a binary variable. And for nodes in different for nodes connected by each edge, you need to make sure that they are assigned to different independent sets encoded by the constraints on the edge. On the right, we see an LLM-generated optimization class. In this case, it's an example of robot maze exploration. Actually, you see a lot of very realistic constraints, such as the robot battery constraint or sensor range constraint. And you also see a few different objectives, such as the exploration cost for the robot to explore the maze, or how much the robot can detect in the maze. So note that this optimization problem does not exist in the C class itself. but rather this is generated through us combining the different C classes through different levels of LLM-based evolution and through telling the LLM to embed the problem into a more realistic scenario. And other than the robot-based exploration example, we see that in our generated class, we see examples such as conference room scheduling, health resource allocation, and so on. So all those examples generated, we find them to be more realistic than C classes and seem to be more interesting and then be more similar to what you see possibly in real world. After we have this synthetic data set, we then study the effect of training a small model, in this case a graph neural network model, and then apply it to different learning tasks. So we study 3 learning tasks in this work. We study integrality gap prediction, which is given an LP solution, linear programming solution. We predict how much gap this LP solution will be to the final integer linear programming solution. So by itself, it's a hard task because ILP is very hard to solve. We also study the task of learning to a branch. In this case, we want to imitate the strong branching experts. And also we study language MILP contrastive learning. So this is to align an abstract MILP instance to a natural language description of the instance. And if we can align this well, this can help non-experts to understand the MILP instance much better. We use a quite standard graph neural network architecture where we embed different variables and constraints into nodes and edges in the graph. And through different layers of graph convolution and attention, we generate different output of different shapes for different learning tasks. And here in the first set of experiment, we do the study where we evaluate our model trained on different training sets into the separate unseen data set. So we compare our LLM-based evolution method with different baselines, including the previous SOTA method that used variational autoencoder to augment the data. We see that our method achieved much better performance across all 3 learning tasks. And further, we study the transfer learning performance to MIPLib. So note that MIPLib is a quite commonly used heterogeneous benchmark to study a lot of this learning-based mixed integer linear programming problems. And again, we see that we are able to attain relatively high performance when comparing with the benchmark. And further, we see that we achieve faster convergence when we fine-tune a small amount of MIPLib instances. Here, we visualize the distribution of the training data from different methods, and we compare that with a MIPLib train. So you can imagine, so you can think about MIPLib train as a very similar distribution training data set, similar to MIPLib test, which we just evaluated on. But to note that we've never seen any of the MIPLib train instances in our synthetic data generation pipeline. We see that comparing with the baseline models, we're able to generate instances that are much closer in distribution to the MIPLib train. So this is partially explaining why we perform better. And finally, we study this question of whether more optimization classes is more important or more instances within each class is more important. So each optimization class means distinct optimization problem, such as job shop scheduling, such as robot-based optimization. But each instance within each class means multiple instances within the, for example, vehicle routing class. So here, across all 3 learning tasks, we see that generating more optimization classes is more important. So probably this LLM-generated optimization class has more diversity, so it makes the learning better than just generating more instances of the same kind. So that's about this first project I'm presenting. So in this project, we developed this LLM-based data synthesis method that we see can be very effective in a lot of learning tasks for mixed integer optimization. So after we finish the previous MILP Evolve project, we move on to a recent hot topic in the LLM for optimization field, which is LLM-based optimization modeling. So this is a task about translating natural language description into optimization code. So we started the project by leveraging a lot of the synthetic data similarly generated in the previous project. But we find that the quality of the synthetic data matters a lot for fine-tuning small LLM models. In fact, if one is not careful, the synthetic data sometimes can even hurt the performance. And this is fundamentally due to the ambiguity in the natural language and or just the challenging nature of the task. Hence, one needs to be careful in cleaning the synthetic data in order to fine-tune LLMs to achieve better performance. So, as I mentioned, in this project, we studied this NL to ILP, natural language to integer linear programming task. And one example of the task is shown on the slides. So suppose you are a business planner. So suppose you are a CEO of a manufacturing company. That you have a planning horizon of 6 months and you have to schedule the production of 3 different products. So you may not be an optimization expert, but you certainly can explain your problem in natural language, such as the description on the left. And traditionally, after, for example, the CEO describes a problem, they hire OR experts to translate the natural language into the solver code. However, although this is typically very accurate, this requires a high level of human expertise and require the human labor, which may take weeks for them to come up with even a solution if the problem is very complicated. So if we can use LLM to automate this step instead, that will be making the process much more efficient. So in the middle, we show an example solution syntax for the LLM. So in this case, we need the LLM to generate an executable solver code. In the example of Gurobi, the LLM needs to know how to import the Gurobi library, generate a Gurobi model, add constraints or add variables and objectives. Afterwards, we can feed this solver code into the Gurobi optimization solver and obtain the solution. Then we can return the solution to the business user. And in this project, we want to make this pipeline more accurate. We want to train an LLM that can do this task very accurately. So there has been a couple of papers about this topic from especially the last year. But we see that when we started this project, we were analyzing a few of the existing benchmarks, such as industry OR or OPT math. We see that there are a lot of problems in the benchmark. We found issues such as missing value, ambiguity in the problem description, or sometimes simply incorrect ground truth. So let me give you a concrete example of missing data. This is found in the OPT math dataset. So in this example, if supply chain planner want to deploy cell tower across a region, and they want to choose different areas in the region to deploy the cell tower. There are 35 areas in the region, but this problem only gives the concrete data as in the constraint for only the first 2 areas. For the remaining 33 areas, the data are just missing. So you can imagine you cannot just give this benchmark problem to LLM expected to solve to get the correct solution because it missed the key data. Yet we find that a lot of previous models, a lot of previous papers in this area were kind of evaluating on this problematic data set. So to ensure the result reliability, the first step in the project is that we manually clean every single benchmark problem to guarantee that they are correct. This is feasible only because there are a relatively small number of benchmark data on the scale of 100 to 300 per benchmark, and we clean 3 benchmarks. However, notably, they still take a long time for OR experts to clean because the problem description sometimes can be really long and hard to understand. And you can imagine the incorrect benchmark kind of destroys the validity of some of the prior research. For example, we have tested on some of the prior SOTA small language models fine-tuned for this task, where we see the performance drastically dropped. And this issue not only exists in benchmark, but we see that it's even more severe in training data. This is because while some of the benchmark instances were generated synthetically, a lot of the training data, if not all, are actually synthetically generated using older or weaker LLMs. You can see problems existing either in problem description, For example, ambiguity or solution code, or a lot of times we see that the linking between the natural language and the code is very problematic. Our initial experiment was heavily bottlenecked by the synthetic data. In fact, we were starting by training a Qwen3-8B model. We see that through SFT and RL, we were able to improve the performance to 47%, but the performance kind of plateaus at that level. And during last summer, when GPT-OSS20B came out, we evaluated the performance with simple prompting without any fine-tuning, and we see that GPT-OSS20B was able to achieve 65%. So this leads to our core research question for this project. Suppose we want to train a very competitive model like GPT-OSS20B. How can we improve the data quality with limited human effort? And here it's very crucial to improve the training data quality. Otherwise, you may even degrade the performance of the model from 65% back to 47%. But the bad news here is that there are thousands of training data. So unlike benchmark that on the relatively small scale, here we cannot hire human experts to clean every single problem. So we need to think about some semi-automated way to improve the training data performance. Our first step is to actually inspect the training data to understand why models were failing. We found that language models, even the very high-capable frontier models like GPT-5 or O4 Mini, tends to repeat similar mistakes for similar problems within the same class. So on this slide, I'm showing an example of traveling salesman problem. So when the problem is relatively small, typically you can use this MTZ constraint for subtour elimination. What the MTZ constraint does is that it assigns this ordering to different nodes in the TSP solution. So basically, we apply a sequence of increasing integers to each city, and the value of the ordering go up by 1. So basically, we introduce this constraint of ui plus 1 less than equal to uj. However, intuitively, this cannot hold when we go from the last city back to the first city. Otherwise, the problem will be infeasible. However, when we examine the LLM responses, we see that a lot of the LLMs make this mistake of not handling this edge case as well. Going from back from, for example, node 5 back to node 0 on this slide, LLM still want the ordering to go up by 1. So you encounter an infeasible problem through the LLM response. The good news here is that explicit hinting can fix this problem. As shown in this example, we provide a hint to LLM telling the model not to apply the constraint to the star city. And we can see from the model response that it takes this hint into account when it generates a new solution and avoid increasing the order by 1 when you go from the last node back to the first node. Hence, the new solution generated with the hint involved is correct. And this observation is key to our data cleaning method. It proves that we can automatically clean the training data set if we can get this sort of class-specific hint to the prompt, and if we can ask stronger model to generate a solution under the guidance of the hint. Let me show you 2 more examples of hints for different optimization classes that we see. For example, for job shop scheduling, when you want to enforce a ordering constraint between job A and job B, typically you have this binary variable YAB, which equals 1 if you want job A to be before job B and 0 the other way around. When we analyze the LLM solution, we see that a lot of times it uses 2 different binary variables, each for each different direction. But there's no linking constraint to link those 2 directions together. Another LLM mistake is that sometimes it codes big M into a constant value, but for different problems, this big M constant value in code may be infeasible. So in our hint, we explicitly tell the LLM to use 1 ordering binary variable for the ordering constraint, and then we give it a reasonable value for the big M so that it don't run into infeasibility issue. Another example is capacitive facility loss sizing. In this example, we have this backlog variable that represents how much you left from the previous periods to the current period. And there's an equation, a balance equation between the backlog variable, the current time steps plan, and the previous inventory. However, a lot of times we see that because there are multiple variables involved in this balance equation, sometimes LLM makes the sign of some of the variables wrong. So in our hint, we give the specific balance equation to make the LLM avoid the mistake. But you can see here, the hint that we give are relatively simplified and abstract. They are not regarding a specific instance, but our goal is that by giving the hint, they can generalize to a bunch of different instances within similar optimization problems. So this is our data cleaning pipeline. First, we do some simple manual work, but only on a small subset of training data. Our human OR expert study how the target model fails to answer the question correctly, and then we create a dictionary of class-specific hints, just as the ones I showed in the previous slides. And know that this is the only step that requires human expertise. Then we can scale up to full training data set. We use this hint to prompt a stronger teacher model, such as GPT-OS's 120B instead of 20B, to regenerate the solution. And through our manual verification of a small set of these generated responses, we see that the LLM can oftentimes avoid making common mistakes. And finally, for quality control, we apply majority voting to select the final solution. So majority voting here means that instead of generate one response, we generate k response and take the most common response to improve the robustness of the LLM's answer. And after we curate this high-quality training data, we perform supervised fine-tuning on this data to get a better model. At inference time, when we serve the model to the users, we apply the same logic. When a question comes in, we first classify the problem type, for example, as a traveling salesman problem. We then retrieve the specific hint we designed for TSP and then inject it to the prompt. This hint warns the model about common mistakes for the optimization class before the LLM starts to generate the response. On top of this, when the compute budget allows, we then apply some standard test time scaling techniques, such as majority voting or self-correction based on solver feedback to further improve the performance. Now let's look at the empirical results. We compare the performance of our SFT model with open source reasoning models under 32B, such as GPT-OS's 20B without fine-tuning, Qwen3 32B, and the previous SOTA method called SRL. We also compare with a bunch of frontier models, such as GPT-5 and GPT-04 mini. The result of our SFT model are shown as the two striped bars, where the first stripe bar is a single turn result of our model, and then for the second stripe bar, we use 5 turns of self-correction to further improve the performance. First, when we compare with other open source models under 32B parameters, which you can see from the lighter bluish bars without the stripes, we constantly outperform them by at least 10%. Next, we compare with frontier models like GPT-5 and O4 mini, shown as the purple dotted bars. With 5 turns of self-correction, you see that we match their performance, sometimes even outperforming, especially for mammal complex. And crucially, our model is only under 20B parameter, which are much smaller than the frontier model. And here, we do a few detailed analysis to study the effects of different components of our pipeline. On this slide, we show a breakdown of the gains from the contribution just from SFT training. We see a massive improvement of our fine-tuned model over the base model, especially for mammal complex data set where you can see a 20% improvement. And also the improvement remains even when we apply the domain-specific hints to the model. Further, we see that our domain-specific hints lead to a significant improvement across a variety of different models and across benchmarks. Here, interestingly, we see that GPT-5, even the strongest frontier model, can benefit a lot from the hints as well. Further, we broke down the accuracy from improvement from hint and SFT by problem type. Here we show 5 most commonly occurred optimization problems And for each problem, the first row shows the base GPT-OSS 20B model without hinting, without fine-tuning. The second bar, we show the performance improvement by adding the hints. And the third bar, we show the further improvement when we add SFT on top of the hints. And we can see significant improvement from both hint and SFT. And finally, we study the performance improvement from test time scaling, and we see that both majority voting and multi-turn correction help the performance. So basically, the more responses you sample, better the performance. The more turn you can correct yourself, better the performance. But this is a trade-off between response efficiency and the performance. Because a lot of times when you deploy the model, you may not have the budget to sample multiple solutions at the same time. To wrap up, in this project, we asked how to train competitive model in a specialized domain of optimization modeling. The lesson learned here is that data quality is crucial. We cannot rely on raw and unverified synthetic data, but by instilling expert knowledge, we can efficiently clean the data, and with that data, we can train a competitive GPT-OSS 20B model to reach frontier models' performance. If you're interested in this project, we have a detailed blog on the Microsoft Research website, and you can search to read. So that's about the end of my talk. Let me talk about a few interesting directions that we are currently considering. So one big challenge for NL to ILP is language ambiguity. As you can imagine, when you interact with users, a lot of times they're not experts, so they don't really know how to use the most precise language to express the optimization problem they have in mind. So a lot of times, LLMs in turn cannot really understand what the user actually means. So this may require multiple iterations and interaction between the user and LLM to concretize the problem. Another direction is verification. Suppose LLM generates a solution. How can we verify it's correct? And if it's not, how can we improve it? For this direction, one may need to train a verifier to provide a guarantee on whether the generated LLM solution is correct or not. Another direction is acceleration. Say a user asks a question for a complicated optimization problem. One cannot just run the optimization solver, wait for 2 hours before the optimization problem is solved, and then give the user a response. Because the user cannot wait for that long. So to this front, it's very important to accelerate optimization and accelerate this LLM plus optimization loop for the user to get the response faster. And in this direction, we've been collaborating with NVIDIA to integrate our OptiGuide framework into their GPU accelerated solver cuOpt. And we have a demo at NVIDIA GTC last year. And finally, we would love to improve the quality of training data and test benchmark for NL to ILP. And we are open to collaboration in this regard. So if, for example, if there's a professor giving an optimization course and they can let each student label a realistic optimization problem, that can be a very valuable data set. And we're open to collaborate if anything like that can happen. So that's it for my talk. Thanks for listening.
Thank you, Sirui. Any questions?
Thank you so much, Sirui. So the first question I want to ask is about the hint you gave for the large language model. So from what you presented us, I think the hint you give are specific for each classes, right? For example, for TSP, you demand like the last node is connected to the node you departed from.
Correct.
So I'm thinking, have you tried giving the large language model some kind of meta or generic hints that increases model output accuracy across all different classes, or does the hints have to be class specific?
So we have tried some simple generic hints, like for it to be careful with the optimization solver syntax, or be careful with a problem optimization variable type, because sometimes it makes mistake to generate a continuous variable where it should be integer. But we see marginal improvement from that. So if you have any idea how to generate more useful generic hint, that would be helpful. Another thing we have tried, so currently we are first classify the problem and then give just a hint of that type to the problem. Another prompting thing we have tried is to give all the hints for all the class, and in a single prompt, let it first classify and then basically generate a solution by looking at all the hints. And we find that that also performed relatively okay-ish. But it seems that for that, you also need to kind of like let the LLM decide which class and which hint you should be applying to, because a lot of the classes a hint generated are actually conflicting. So if you cannot decipher which class you belong to, you may get the wrong hint that makes the performance worse.
Okay, so here is a somewhat relevant idea about this. So have you tried to design like an agentic workflow to have a checker agent to see the output of the large language model and ask it to check if this is a valid model or not?
So I guess something that we're currently pursuing is more, as along the line of what you said, like given an LLM response, comparing with the ground truth, let the agentic framework decide whether this is correct or not. If it's incorrect, we kind of figure out a hint from that. That's something we've been trying. We see some improvement, but doesn't seem to be as effective as manual hint here. I know there are related work like alpha, OPT, and similar papers about automatic hint generation. That's also a very interesting field. Could be for future work, future investigation.
That answers my question. Thanks so much.
Thanks.
Hello, you mentioned earlier on that through observation, you would observe the LLMs keep making the same mistake and then add explicit hints in the prompt to address this. Is it obvious a priori that the mistakes fall into discrete categories? Is there a systematic way to say this mistake is occurring very frequently and at scale versus being a one-off issue? How is it, at a systematic level, do you measure this?
Yeah, so because this hint generation requires some sort of human label, we only looked at a subset of training data, so around maybe 10 problems each class. So in that case, we didn't really generate many hints, but we do see that a lot of the classes make similar mistakes. But this could be due to that the training set and the benchmark currently are on the relatively easy scale. So I can imagine if you have a more realistic data, maybe sometimes you make an instance-specific problem. So to that front, we have some, as I mentioned, we have some automatic hint generation attempts. We see that when we do automatic hint generation, sometimes LLM give you a lot of suggestions, some are redundant. So for that, some from the hints you need to throw away because it's very instance-specific. But if we just use human expertise, most of the time we kind of, at the labeling stage, we already kind of throw out all the too specific hints and not generate them already. Yeah.
First of all, thank you very much for the great talk. I just have a really quick question, maybe a little bit philosophical, about this idea of combining expertise with open weight large language models. So do you agree with Rick Sutton's his essay called Bitlessing? The idea is that eventually domain expertise probably doesn't matter, or you need just to keep scaling and you get better and better performance?
Definitely, if you have a lot of data on the scale of the amount of data they used to train GPT-5, I would say probably this can be replaceable. And also, if you look at the result, GPT-5 already achieved a very good performance here. So, we agree to some extent, if you have a large number of data, probably if you train on adjacent field like coding, in this case, maybe domain expertise doesn't matter that much on a large scale. But at the current stage, if you look at small models, it seems that this domain expertise still helps. But who knows, like they could use our open source hint to train their next model. So when the next model release, even small, we may not use, the current expert hint may not be useful anymore.
Awesome. Thanks for the great talk. So a lot of the effort, I guess, in the second half of the talk was on this like data quality issue. And I'm wondering what sort of kind of filtering you guys used for the first half of the talk for the generating new synthetic kind of data.
Can you repeat?
Yeah, like do you have any guardrails on the synthetic data generation you mentioned in the first half of the talk to ensure that it also has kind of those quality bars?
Yeah. So I guess when we approach this synthetic data generation project, the tasks we do are in some sense easier because here we only work with code, like the optimization instance themselves, but doesn't really work with natural language. So you see, like for the NL2 ILP problems, I think a lot of the benchmark or training data issue come with the natural language or the linking between the two parts. So in this project, we kind of like didn't really look at that aspect because we don't study the natural language. But yeah, that's kind of issue that emerged when we start the last project I mentioned, when you play with natural language.